In this topic, we're going to start considering how we might find the area under this curve between x equals a and x equals b. So if we had the function y equals f of x of the curve, and if we knew how to integrate f of x, we could use the integral from a to b of f of x with respect to x. A problem would happen if we were not able to integrate the function f of x, and in this case we would consider how else we might find an approximate value for the area under that curve. We could approximate the area using rectangles, so we could split the distance from a to b into a certain number of rectangles and then model these under the curve. However, you can see this isn't going to give us a very good approximation of the area because we've got quite a lot of space missed out. In this case, we would get quite a significant underestimate. So perhaps a better shape to use might be a trapezium instead. So this is going to lead us into what we call the Trapezium Rule, which is a numerical method for finding an approximate value for an integral, which represents the approximate value for the area under a curve. So suppose we start with the area here from A to B, split into 3 trapeziums. You can see it fits much more closely to the area that we want. Each of these trapeziums are called strips. So in this case we have n of these strips. And the x values for the start and end of each of the trapeziums, we start labelling them x0, and we label them x1, x2 up to xn. So for example, in this case x0 is the value of a, we then have x1, x2, x3. In this case, because we have got 3 trapeziums, x3 is the final x value, and that is b. So because these trapeziums have all got an equal width, we can find the width of each one by dividing the distance from A to B by the number of strips we have, which is n. So h can be calculated using the formula b minus a over n. This gives us the width of each trapezium. And the number of these x values is always one more than how many strips there are. So in this case we can see we've got 3 strips, but we actually have 4 x values. So the y values are going to be the heights of each of the sides of the trapeziums, and they correspond with the x values. So we call these ordinates. So for example, y0 is the height of the trapezium at x0, then y1 is the height of the trapezium at x1, and so on up to yn. And if we knew these y values, then we could use the area of a trapezium formula, which is half of the sum of the parallel sides multiplied by the distance between. So in this case it will be a half of h, the distance between, multiplied by yk plus 1. That's the sum of the 2 heights of each side of the trapezium. We can find the y values by substituting the x values into the equation of the curve, and that will tell us what y is at each point. So in this case, if we were to find the total area of all of the trapeziums, we could use the formula for the area of a trapezium and add them together. So the first trapezium is going to have an area of a half h and then y0 plus y1. The second trapezium is going to have an area of a half h, y1 plus y2, and then continuing on we get the area of the third trapezium, a half h, y2 plus y3. And you can see we can simplify this a bit. As you can see, there's a half and a h in each of these terms. So simplifying these together, we get, and factorising, we get a half h, y0 plus y1 plus y1 plus y2 plus y2 plus y3. As you can see, some of these y values appear twice, y1 for example and y2. But some of them, the ones on the end, y0 and y3, only appear once. So we can group together the ones that appear twice. We get a half h, and then in brackets we get y0 two lots of y1 and y2, and then y3. This will give us an approximate area of all of the trapeziums added together. Suppose we had decided to use 4 strips instead of 3. Obviously we would have had a different h value because the strips would all have been narrower. Would have been dividing by 4 instead of 3. So the formula would have had an extra trapezium added onto the end. So we would have ended up with a half h and then y3 plus y4. This time when we factorise, we can still pull out a half h, and this time we've now got 1 y0 and 1 y4, and we've got 2 of each of the y values, the ordinates between those. So we get an area of a half h, y0, 2 plus y1 plus y2 plus y3 plus y4. We could generalise this for any number of trapeziums we like. So if we use n strips, this would give us a total sum as follows. Again, this total sum always has a half h in each of the trapezium formulas, so we can pull that out to the front. And as you can see, the first ordinate and the last ordinate only appear once in the sum, but all of the ordinates in between, y1, y2, y3 and so on, all appear twice. So we get this formula, a half h, y0, 2 lots of all of the interior ordinates, and then yn. So this is given to us in the formula book as the trapezium rule. It's written slightly differently. For example, the 2 end ordinates are just put together here at the beginning. So this tells us that the integral of y, which is just the what the equation is, between a and b, they're the 2 endpoints, is approximately equal to, so it's not exact, that's why we've used the approximately equal to symbol, a half h, where h is the width of the trapeziums, multiplied by the end ordinates, y0 and yn, and 2 lots of all of the ordinates between, y1 plus y2 plus y3, all the way up to yn minus 1. Obviously the number of y's in here depends on how many trapeziums we've used. H is always calculated by b minus a, so the difference between the 2 endpoints on the integral, divided by n, which is the number of trapeziums we want to use. This is called a numerical method because it finds a numerical approximation to something that we might struggle to do algebraically. For example, if the function is too difficult to integrate. And we can improve how good the approximation is by increasing the number of trapeziums that we use. So more strips gives a better approximation to the area. So here's an example. We're going to use the trapezium rule with 6 ordinates. Remember that the ordinates is how many x values and y values we want to use. So 6 ordinates would actually only be 5 trapeziums or 5 strips. We want to integrate from 1 to 3 the function e to the 2 sine x. This is obviously not a function that we know how to integrate, so this is why a numerical method is important. It's also important to know that anything involving the trigonometric functions, sine, cos and so on, if we're integrating or differentiating any of those, must be in radians. This is because the rules that we know that we'll come to later on for integrating and differentiating trig functions only work when the functions are in radians. So first thing we're going to do is find out what the value of h is going to be. Remember that h is the width of each of the strips. So 6 ordinates tells us there's going to be 5 strips, so n will be 5. The difference between a and b, the endpoints, is 3 minus 1, so 2, and we're going to divide that by 5. So that gives us 0.4. This means that there's going to be a width of 0.4 for each of the trapeziums. At this point, it's important to draw a table with the x and y values in. This is so that you've then got the values to substitute into the formula when we come to it. Make sure that your table has the correct number of x and y values, and make sure that your first x value is, in this case, 1, and your last x value is 3. it should then go up nicely in steps of 0.4. You can also use the table function on your calculator for this. Just make sure that if you're using decimal values, that you use at least 2 more decimal places in all you're working out than the final answer is going to be, so that you don't get any round off errors. So the x ordinates, x0, x1, x2 and so on, are going to start at 1 and go up in steps of 0.4. It's going to end when we get to 3. So 1.4, 1.8, 2.2, 2.6, 3. This does fit in with what we were told. We were told there were six values, 6 ordinates, and we do indeed have 6 x's there. We're now going to use the function e to the 2 sine x, substituting in each of those x values to give us y. So here we have the y values. As I previously mentioned, if you're going to be giving your answer to, for example, 2 decimal places, you would always do your working out to 4 decimal places and so on. Always use slightly more decimal places or significant figures than the final answer. So we can now use the trapezium rule from the formula book. Substituting in the values, we have a half h, so half of 0.4, multiplied by y0 plus yn, which are the 2 end values for y. They're the 2 that only appear once in the formula. And then 2 times the sum of each of the interior ordinates, so 2 times the sum of these 4 here. Don't forget to put enough brackets around to make sure that everything is then multiplied by the half h at the front. This should come out as 10.15. Now, this is an approximation for the integral. At this point, it's a very good idea to calculate the actual integral using the integration function on the calculator to make sure that the numbers look approximately right. So put your calculator into radians and use the integral function, which is just below the menu button on your calculator. Substituting this in should give you an approximate value for the integral that we were trying to find. So substituting in e to the 2 sine x. You won't get any actual marks for calculating the exact value, but I can see that putting this into the calculator gives me 10.267. This is very close to 10.15, so this suggests that my calculation for the trapezium rule is correct. This is just a good way of checking your answer in an exam. So if we were to look at a graph, so look at the graph of a function and to draw the trapeziums in, we can see in this case there seem to be some areas here that are not covered by the trapeziums that would be included in the original area. There's also another area here where this trapezium has covered that area, but actually it wouldn't be included in the integral. However, on the whole, it looks as though there are more gaps, more bits missed out compared to the overestimates here. So on the whole, it looks as though the answer we have got will be a slight underestimate. So the trapezium rule answer will be slightly smaller than the integral answer. You can see here this is because the graph's concave, so therefore the graph protrudes above the top of a trapezium. You can see over here the graph is convex, so the trapezium is slightly larger than the area we're trying to find. But on the whole, we have got a slight underestimate. This fits in with the fact that when we calculated the answer on the calculator, we did get a slightly larger answer for the integral compared with the numerical method. Now complete exercise 5.1 on page 377.